Courses in the cement industry. Present to you. In this course, we will cover everything about clinker burning. The burning process is carried out in the rotary kiln and calciner, while the raw materials are rotated at 1 to 2 rpm at its longitudinal axis. The rotary kiln is made up of steel tubes, having the diameter of 2.5 to 3 meter, and the length differs from 90 to 120 meter. The inner side of the rotary kiln is lined with refractory bricks. There are 3 stages to clinker burning process. A. Calcination. B. Fuels management. C. Clinker cooler and storage. Clinker burning process can be defined. The clinker burning process is a high-temperature process resulting in the formation of nitrogen oxides, NOx. The amount formed is directly related to the main flame temperature, typically 1850 to 2000 degrees. Introduction. Our objective: to prepare a finely ground, homogeneous mix of the components, which results in good burnability. Stages of the clinker burning process. 1. Quarrying. 2. Blasting. 3. Excavation. 4. Crushing. 5. Dosing of components. 6. Grinding. 7. Homogenization. 8. Burning. What are the main components of clinker manufacture? Calcareous material, consisting of limestone, marl limestone, calcareous marl. The chemical symbol CaO. Alkaline compound. Argillaceous material, consisting of marl, argillaceous marl, marl clay. Clay. The chemical symbol SiO2, Al2O3, Fe2O3. Acidic compound. Clinker. The chemical symbol and proportions of the components: C3S, 55 plus 10. C2S, 25 plus 10. C3A, 9 plus 4. C4AF, 11 plus 4. Facts. 1. Kiln system has to be operated continuously to assure its economic success. 2. Chemical process does not change from wet to dry system. 3. Clinker burning involves transformation of natural mineral to a blend of synthetic minerals. On firing, the raw mix decomposes and combines to form new chemical combination. Natural minerals. Effect. Temperature with time and pressure. Be the product of the reaction. Synthetic hydraulic minerals. Noticeable. The reactions are different and time-consuming. Basic types of reactions taking place during process. A. Disintegration of original minerals. 1. Mechanical crushing and grinding. 2. Thermal decomposition. 3. Structural rearrangement on heating, polymorphism. For example, 1. Structural changes. See the figure. Low quartz. A change occurs at a temperature 573 degrees. Change occurs to high quartz. Basic types of reactions, taking place during process. B. Formation of new mineral product. 1. Occurrence of intermediate. 2. Genesis of clinker mineral. 3. Crystallization of liquid phase. Raw mix. A change occurs at a temperature 1450 degree. Using an oxidizing agent. Change occurs to clinker. Process related to preheater and kill zones. Suspension of material in hot gases. Preheater cyclones. Material. The change occurs at a temperature 820 degrees. The change that happens. Evaporation of free and absorbed water. Inside kill. Transformation of dry particles into clinker nodules in the vicinity of liquid phase. Process related to preheater and kill zones. The process includes 1. Chemical reactions. For example, formation of C3S and C2S. 2. Physical properties. For example, agglomeration of particles to form nodules, ranging from 2 to 20 mm. The properties of cement does not only depend on potential contents of minerals, but also on the degree of completion of these minerals. Rotary kiln model. Without taking preheater in consideration. The hot part of kiln model can be divided into 1. Calcining zone. 2. Heating zone. 3. Liquid zone. After liquid zone start. Burning zone. 5. Maximum temperature. 6. Cooling zone. The figure shows the path of the material entering the preheater from the top. It also shows the path of air entering the preheater. Also shown are the temperatures inside the preheater for each zone, as follows. 1. Drying zone. The temperature is in this zone, 100 degree. 2. Heating zone. The temperature is in this zone, 700 degree. 3. Calcining zone. The temperature is in this zone, 1100 degree. 4. Sintering or burning zone. The temperature is in this zone, 1450 degree. Calcining zone. What happens inside the calcining zone? 1. CO2 evolves, temperature rises rapidly, at complete decarbonation. 2. C2S, starts formation. 3. Complete decarbonation of kiln feed, is a prerequisite before entering burning zone, disturbances occurs. 4. Although, C2S is exothermic, yet decarbonation needs heat. 5. The particles fluidizes, due to high partial pressure. Heating zone or transition zone. What happens inside this zone? 1. Temperature of material is between 900 to 1300 degrees Celsius. 2. Bed of kiln charge is dark. 3. Temperature rises quickly as decarbonation is finished. 4. Intermediate phases takes place, they are stable within narrow temperature limits. 5. 1/3 of the coat of kiln is located in this zone. Liquid zone. Begins at 1300 to 1350 degree. Liquid phase is formed, it depends on chemical composition of kiln feed, and has minor increase by temperature. Nodulization of clinker starts. Size of nodules depends on quantity and property of liquid phase. C3S starts formation. In order to secure good nodulization, liquid zone should be long. Relation between liquid phase and aluminum modulus, silicate modulus, lime saturation factor. In this chart explains 1. Curves 1, 2, and 3. Shows the change of liquid phase with temperature. When reducing aluminum modulus, silicate modulus, and lime saturation factor. 2. Curve 1 shows that the melt content decreases by reducing aluminum modulus from 2 to 1.6. 3. Curve 2 shows the melt content increases for all temperature by reducing the silicate modulus from 3.2 to 2.6. 4. Curve 3 shows that the melt content slightly increases at all temperature by reducing lime saturation factor from 98 to 90. This diagram explain clinker minerals as function of lime saturation. This diagram explain clinker minerals as function of silica ratio. This diagram explain clinker minerals as function of alumina ratio. Maximum temperature zone. 1. When C3S reaches its critical value, nodulization stops, and maximum temperature begins. 2. The dominant process is the C3S growth. 3. As the material passes the flame, its temperature decreases, and phases solidifies. Cooling zone, AZ. 1. It starts when the material starts to solidify, due to cooling of clinker liquid. 2. The slower the cooling, the greater the decrease of C3S. 3. The liberated CaO combines with Ca forming C3A, 1/3 of C3A is formed in cooling condition. 4. The conversion of C3S to C2S affects grinding. Kill zones in relation to alite formation. In this chart explains. In maximum zone formation of C3S is rapid due to high temperature and frequent contact between CaO and C2S. Kill zones in relation to alite formation. Divided into two types. In this chart explains. Difficult burnable. In this chart explains. Easily burnable. Relation between the zones and burnability. The most important zones for good agglomeration of material are 1. Heating zone. Must be long to ensure nodulation. 2. Liquid zone. Reduction of lime saturation factor, aluminum modulus, and silicate modulus, produce easy burning. In this chart explains. Complete overview of reactions, which are occurring inside the kiln system, may be illustrated on the following diagram. Chemical transformation. Certain physico-chemical process takes place during heating raw material. 1. Dehydration of argillaceous mineral. 2. Decomposition of carbonates. 3. Reaction of solid phase. 4. Reaction of solid phase in presence of liquid phase. Chemical transformation continue. The above mentioned factors are influenced by 1. Chemical composition. 2. Mineralogical factors. 3. Physical factors, fineness, particle size, homogeneity. Changes in minerals taking place during clinker burning. 1. Carbonates decomposes at 600 to 900 degrees. 2. Quartz and clays decomposes at 500 to 800 degrees. 3. CaO plus SiO2 equal C2S. 4. C2S plus CaO equal C3S. 5. Ca plus 2CaO equal C3A. Decomposition reactions. 1. Dehydroxylation of clay. 2. Decarbonation of simple carbonates. 3. Decomposition of complex carbonates. 4. Decomposition of alite. Decomposition reactions. Example 1, dehydroxylation of clay. 2SiO2. Al2O3. 2H2O. Designate, kaolinite. At 500 to 600 degree. Result. 2SiO2. Al2O3 plus. 2H2O. Designate, metakaolin. 2SiO2. Al2O3. 2H2O. Designate, kaolinite. At 500 to 600 degree. Result. 2SiO2 plus. Al2O3 plus. 2H2O. This material, amorphous material highly reactive, and unstable. Decomposition reactions. Example 4, decomposition of alite. C3S. If the temperature less than 1250 degree, result from C2S plus CaO. Maximum rate of decomposition occurs at 1170 degree. Decomposition of alite into belite, CaO. In this diagram, it is divided into 1. Aluminate. 2. Fine mix of belite, secondary, plus CaO free. 3. Well crystallized. C4AF. 4. Alite, C3S. 5. Belite, C2S primary. Notice. Cooling rate must be fast. Classifications of mineral reactions. Types. 1. Structural change. 2. Decomposition reactions. 3. Combination reactions. Classifications of mineral reactions. Types. Combination reactions. 1. Belite formation. 2CaCO3 plus SiO2 at 800 to 1200 degree. Result. C2S plus CO2. 2. Alite formation. C2S plus CaO at 1250 degree. Liquid phase. Result. C3S. Alite formation from CaO, belite. See in this diagram. Quantity of liquid phase should be 20 to 30%. Chemical reactions leading to refractory damage. SO3. Attack on castables. 2Ca, Al2, O3, castable. plus SO3, from kill gases. Result: CaO, 2Al2, O3 plus. CaSO4. CaSO4 plus. 2H2O. On cooling during shutdowns. Result: CaSO4 plus. 2H2O. Result of shutdowns: 1. Destructions of bonding. 2. Loss of strength. Chemical reactions leading to refractory damage. Alkali bursting of alumina refractory. 3Al2O3. 2SiO2. He is called mullite. Plus 3K2O. Plus 4SiO2. Result: 3K2O. Al2O3. 2SiO2. He is called calcilite. Delta volume equal plus 29%. Al2O3. He is called bauxite. Plus K2O. Plus 2SiO2. Result: 3K2O. Al2O3. 2SiO2. He is called calcilite. Delta volume equal plus 2.5%. If necessary to install high alumina refractory, in zone where danger of alkali bursting, use bauxite-based rather than mullite-based refractory. Factors affecting kinetics of the reactions inside kiln. 1. Fineness. 2. Particle contact. 3. Liquid phase quality and quantity. 4. Distance between reactants. All of these factors fall into kinetics. Factors affecting kinetics of the reactions inside kiln. Fineness. In this diagram, small particles faster the reaction. In this diagram, big particles slower the reaction. Rate of various reaction types. See this table. Thermochemistry of clinker formation. 1. Exothermic reaction. Heat liberated. 2. Endothermic reaction. Heat absorbed. Reasons for build UPS. 1. Build UPS are CaSO4 solid and alkali sulfates. 2. Alumina ratio too low. 3. No SiO2 free. 4. Clinker sticking due to the formation of alkali chloride. Reasons for volatilization and ring formation. 1. High alkalis as sulfates. 2. High chloride from alkali chloride, which is volatile and cause ring formation, by acting as a catalyst forming spurite, 2C2S. CaCO3. Reasons for coating. 1. High alkalis. 2. High sulfur cause excessive liquid formation. Thank you for watching, and I hope these courses are helpful to everyone. Subscribing to this channel Cement Industry Courses would be appreciated. Thank you.